Hi friends, welcome to follow up. Let's have a look at problem 823, binary trees with factors. In this video, we're going to present a solution based on dynamic programming. So actually this problem is very interesting in the sense that first it's related to the binary tree data structure. Secondly, we can practice dynamic programming. So our plan for this video will be the following. First, we'll digest the problem, and then we do the simple analysis, and finally we share the code. Actually, the code is also very short. So first, let's look at the problem statement. So given an array of unique integers, notice that the integers or the numbers in the array are unique values. So where each integer, array I, is strictly greater than 1. So then we make a binary tree using these integers, and each number may be used for any number of times. So we can use it once or multi times or even 0 times. So each non-leaf node's value should be equal to the product of the values of its children, right? So this sentence actually is defined in a recursive fashion, right? So here, what we want to find is the number of binary trees we can make. And the answer might be very large, so we modulo a big prime number. So let's look at the two examples here. So first, each single number itself can serve as a binary tree, but a single node, right? So 2 can be a single node binary tree, 4 can be a single node binary tree. So we have 2 trees already. So here the output is 3. 3 because that we can use 4 as the root value, and then we use one left child and one right child, both with value 2, because 2 times 2 is 4, right? So notice that the left child and the right child have the same value in this example. So similarly, in example 2, the return is 7. So first we know we have 4 trees using single value. So we have 2, 4, 5, 10. So then let's look at 4, right? If we use 4 as a root value, then we can have 2, 2 also. But this 2 and 2 are the same, right? So in this regard, it can only provide us one tree, right? So now if we look at 5, because 5 is a prime number, right? So it cannot produce more trees. So just have a single node with root value 5. So now look at 10. So 10 is a product of 2 and 5. So right, we can use 2 as left child, then 5 as right child. If we use 5 as left child, then we have 2 as right child. So this provides us 2 binary trees. So therefore, in total, we have 7. So with that said, let's look at the constraints. First, the length is bounded above by 1000. So basically, this means that even if we use square term complexity solution, so the test will be passed. And also, this is the range. It's greater than or equal to 1. This is what we want to emphasize. Actually, the last 2 items in the constraint are covered in the first paragraph, right? So with that said, let's look at the coding part. So here we are going to use dynamic programming. So based on the two observations. First, we know that each node, each value can provide a single node tree, right? And another thing is that let's see, we have a root value. Let's see if root have value, say basically root value, it should be equal to the value of left child and the right child, right? So root left value times root right value, right? So this is the case. So now let's look at the coding. So we can actually use DP. So because all these values are unique, we can use this DP and a value to notice that the number of binary trees rooted at node with the value being this value, right? Then the case thing is how to do this update, right? So now let's look at code. So here I have write this array to be capital A just for convenience of writing. So first I'm going to initialize a DP table. So here I'm using dictionary, but sometimes you can use list or multi-dimensional list. But here, because of the uniqueness of these integers, it's good to use this as a key and the count as values. So in order to better do the counting, because we can first count the number of trees rooted at a smaller value and then go to larger value, because this relation should hold, and the root value should be at least no less than the left child or right child. And if you take into consideration of this assumption, the root value will be larger than the child values or the children values. So for this, I'm going to do a sort. I'm sort this in place. And then we are going to do this update. So basically for a number in A, right? So what we want to find is the number of binary trees rooted at this one. So basically it's a sum. So we want to check within the current case of the DP table. So let's say B, right? So we want to find how many of those can be used as left child. If we use this as left child, then the number of right child would be something like this. So we are going to compute A over B. So if A over B is not in the DP table, it means that B cannot be used as a left child. And then we're going to get using this get to treat this case. We're going to have a 0 right in this case if A over B is not a key. And then this is a comprehension. So for B in DP, then if A over B equals 0, right? But notice that each of the unique values corresponds to a single node tree. So we need to count that. So with that done, so we can do the return. So we want to return the DP values, right? We only care about the values. And then we need to modulo a big constant, that is 10 to the power 9 plus 7. So before we make any comments, let's first do a test. Yeah, it passes the first example. So now let's look at the generic case. Yeah, it passes all the generic cases. So in order to better understand this problem, so let's see first here, let's say if we have root 10, so we can use 2 and 5 as left child and right child, or reverse, use 2 as right child. But here in this one, DPB get this A over B. Actually, we checked both, right? For example, you can think of A equals 10. If B equals 2, so here is 5. You checked 2 times 5. And B is 5. Here will be 2. You checked both. So it means that our logic covers the situation. But if it's for this case, 4. So basically, essentially check once, right? So this is the one thing. Another thing is that we see a number of times this number. So first I want to mention that this 10 to the power 9 plus 7 is a prime number, and it suits a 32-bit integer. So I guess that's the meaning for this one. So you modulo this big prime number, then you're going to get something smaller. So that's the thing. And the second part is that in order to better understand this, we can print out this DP table. Let's see, we can print out this DP table. So it's DP. So let's look at the first example. So at 2, we are going to have 1 binary tree. At 4, we are going to have 2. So now let's check this case. So at 2, we have 1. At 4, we have 2, right? So now let's look at the second example. Let's check this case. So let me first specify this for 2, 5. So we have 1 at 2, right? We have 2 at 4 because 4 itself plus 2 times 2, right? So at 5 we only have 1, right? At 10 we have 1 that is itself. Then we have 2 times 5 or 5 times 2, that is 2. In other words, it's 3. So overall we have 1, 2, 1, and 3. So this 4 plus 3, that is 7. So now let's print out this and compare with this result, right? Yeah, at 2 we have 1, at 4 we have 2, at 5 we have 1, and 10 we have 3. So with that said, I guess that's about it for this specific problem. So if you want to check the temp complexity, so overall it's O of n squared, right? Because this is one loop, and the inside is also a loop. But here basically you want to check for each number how many factors it has in this list. So it can be slightly better, but overall it's O n squared. So with that said, I guess that's about it for this video. Thank you.